Ladies and gentlemen, welcome to today's edition of Physics. In this video, you are going to see voltage, current, resistance, and power, which I've labeled VERT. Now you know why I did that. We're going to start off looking at voltage, but in order to look at voltage, I want to revisit our cliff that we had in first semester. Here's you at the bottom of the cliff. You're smiling. Why are you smiling? Because you're doing physics, and physics is fun. Woohoo! Here's me at the top of the cliff. I'm smiling. A lot of people say out loud, you're smiling because you're doing physics. No, I'm smiling because I'm about to drop a heavy mass on your head. When we go to look at the amount of energy that this mass has, the energy is equal to mass times gravity times height. We remember that from first semester. One thing that I really didn't talk about much in first semester was this term. If I group those G times H, I could have called that a gravitational potential. Gravitational potential is saying the height of our cliff. For any cliff height, a different mass will have a different energy. So if we revisit that cliff, if I drop a bag of marshmallows on your head, doesn't have a lot of mass, doesn't have a lot of energy, you're not going to get too upset about that. However, if I go to Lowe's hardware store, Lau's hardware store, and I drop a sack of cement on you, a lot of mass, a lot of energy, but they both have the same potential. Potential is the ability to give energy to a mass. For a certain cliff, this potential says for more mass, I get more energy, but everything has the same potential. At the top of the cliff, every mass has the same potential to gain energy. This is the potential to gain energy. Are gravitational potential and gravitational potential energy the same thing? Clearly they're not. This is the energy an object has. This is the height of my cliff in a gravitational field. This is the potential. This is the potential energy. Different birds, man. Different birds. I'm going to use that analogy with electrical potential. Electric potential energy is the charge times the electric potential. Just like gravitational potential energy was the mass times the gravitational potential. Here we have mass, here we have potential, there we've got energy. So the potential gives a mass some amount of energy. The potential gives a charge some amount of energy. You can think of electric potential as our electrical cliff. When we bring this electron up to the top of our cliff, here I've got a 6-volt potential cliff. This electron up here now has a certain amount of energy. The potential is different than the potential energy, but they are related. So the potential energy is equal to charge times the electric potential. Potential energy is equal to mass times the gravitational potential. Bring a mass up to a cliff, it gets a certain amount of energy. Bring a charge up to a cliff, it gets a certain amount of energy. So a battery is an electrical cliff. It brings the electrons up to a certain amount of potential energy because those electrons have a charge. Electric potential is a synonym for the word voltage. Saying something has a lot of voltage and saying it has a lot of electric potential, two ways to say the exact same thing. Voltage, if I were to have you define it on a test, voltage is the amount of energy we could give a charge. Because if I divide Q over to the other side, voltage is energy per charge. So voltage is the amount of energy we could give a charge. Is it the same thing as energy? Clearly it's not. Potential and potential energy are two different things. Voltage is measured in volts. Doesn't mean anything, just honors this dead scientist. His name was Volta. 1 volt, 10 volts, not a whole lot. 1,000 volts, that's a lot. So the symbol is a capital V, and again, I put these little lines on my V to denote that it's a capital as opposed to my lowercase v's, but since I write in all capitals anyways, that's how I distinguish it. So we could get a battery. Say the voltage of our battery is 1.6 volts. And everyone would know what we were talking about. Current is defined as the flow of electrons. So voltage was the energy we could get electrons to run around inside a circuit. Current is the flow of electrons inside that circuit. The symbol for current is the capital I, and current is measured in amperes, which we often shorten down to amps. I'm lazy, so I'll often write that as a capital A. So the current is equal to 1 amp. 1 amp is defined as 1 coulomb of charge flowing per second. If you ever experience a current of 1 amp, you won't experience it for very long because chances are you'll be dead. A lot of times students ask me, what is the voltage that's dangerous? No. There is no danger voltage. I've raised myself up to a potential, to a voltage of 150 million volts before, and it's just fine. Voltage isn't a problem. Voltage doesn't harm you. What harms you is the current when these electrons actually start to flow. And in most humans, 0.7 amps is fatal. If you have 0.7 amps across your heart for more than a second, you're going to die. Now, that's on average. I don't recommend that you start hooking that up and start raising the current up a little bit and up a little bit and up a little until you find out what kills you. Don't do that. Just know that if you got an amp, that's a lot. That's a screaming lot of current flowing through a circuit. Resistance. Opposition to current flow. Anything that makes it harder for the electrons to move through the wire is resistance. The symbol for resistance is a capital R, and we measure resistance in ohms. 1 ohm is not a lot of resistance. 1,000,000 ohms is a lot. Every wire has some, every electric circuit has some, every electric component has some resistance. Our job is to minimize the resistance to maximize the current that flows. How much resistance is in your circuit depends on 4 things. The first one, what kind of material is your object made out of? Conductors don't have a lot of resistance, insulators do. So if you've got a copper wire, it's got a little resistance. Second, what is the shape of your wire? A skinny wire has more resistance than a fat wire. The analogy that I use is imagine that you're trying to walk through the halls of school. If the school is narrow, if the hallway is narrow and you got a bunch of freshmen in the hallway that you're trying to get through and they stop suddenly and you got to walk around, it's easier to get down a wide hallway than a narrow hallway because you can weave in between the freshmen. The size of your wire matters. How long is your wire? Like a short wire has less resistance than a long wire. Long wires have more resistance. Again, imagine the hallway. If you're trying to get down the hallway, it's easier to go a little distance than a great big distance if you got all these freshmen in your way. The last one is the temperature. At low temperatures, the freshmen are kind of stationary. They're not moving real fast, so it's easy to weave in between them. At high temperatures, that's freshmen that have just come back from lunch, so they're all sugared up. They ate like 10 bowls of ice cream and chugged Mountain Dew, and they're bouncing off the walls all across. It's hard to get down the hallway when they're acting all goofy like freshmen do. So the resistance depends on what type of material it is, the thickness of your wire, the length of your wire, and the temperature of your circuit. Ohm was the scientist that put all this stuff together, and he looked at it and he came up with the relationship between voltage, current, resistance, and current. This seems to make sense to me. Voltage is the energy we could get to push charges around. So if I've got more energy per charge, I'm going to have more charges able to run. That seems to make sense to me. If I can put more energy in, I get more stuff moving around. All right. Resistance, opposition to current flow. If I have more opposition, then I'm going to get less current. As the resistance goes up, the current goes down. That seems to make sense to me. Think of resistance as the snow driving. If you've got a little bit of snow, a lot of people can drive. If you've got a lot of snow, a lot of people don't get in their cars and start to drive. So as the resistance goes up, the current goes down. Those seem to make sense to me. This is Ohm's law. But just like we had in first semester, when we had acceleration as net force over mass, and we rewrote that as F equals ma, we will often rewrite this as V. But we know that it's really the current that is affected. The voltage and the resistance affect the current, even if we write it as V, because it's easier to say V as opposed to I equals V over R. That's Ohm's law. Power, same thing that power's always been. It's the work or energy expended per time. We know that power is measured in watts, so 1 watt is 1 joule per second. All right, how does that look in an electrical circuit if we're talking about electrical energy as opposed to mechanical energy, which we looked in the first semester? It's no different at all. It's just a different equation. The power is equal to I times V, PIV. So we're going to use VIR and PIV a lot. But even now I can hear people say, but wait a minute, if V equals IR and P equals I times V, can't I plug in I times R for V? Well, yeah, you can. And we get P here. P is equal to I squared times R. But wait a minute. Right now I can hear other people saying, but if I equals V over R, can't I plug that into I? Well, yeah, you can. And you get PIV for zero. I don't know what that is. But yeah, those are all interchangeable equations. You can use whatever one you want based on what you know in the problem, but you can use them all.